Right, so this video will be an add-on to the other video I made about orbital motion and conic sections. Link in, yeah. And in that other video, I just wrote down the equation for two masses interacting through gravity, like here or something. Then I just said that it can be solved and moved on to the solution and explained the solution. And here in this video, we are going to actually solve it and actually do it. All right, pumped, so psyched, let's fucking do it. So we've already talked about conic sections in the main video, but here we need to be more quantitative and more rigorous, so we need a mathematical definition. The thing is that in polar coordinates, the equation for all conic sections have the same form. Looks like this. Epsilon is the eccentricity of the curve, essentially how much it is squeezed. And k is a scaling factor. And it turns out that the eccentricity epsilon is the relevant factor which will decide which form of curve you get. So for epsilon equal to 0, you get a circle. Between 0 and 1, you get an ellipse or different ellipses. For epsilon equal to 1, it's exactly the parabola. And for values bigger than 1, greater than 1, you get hyperbolas. And if all goes right, I will have an animation right here. A beautiful animation. So let's start with our original equation, the Lagrangian for the system. And this describes a system of two particles with mass mi and position ri interacting with each other through gravity. And to get this equation, you just do what you always do with Lagrangians. 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 You just take the kinetic energy minus the potential energy, and this is known for gravity. And the following steps might feel like quite a ride, but the idea is always the same. You always take some symmetry of the system and use that to simplify your equation down to the point where you can finally solve it. Actually, all symmetries are deeply connected with some conserved quantities, and we will use all of these in the following. First, symmetry of translation from the conservation of momentum of the center of mass. Second, rotation symmetry from the conservation of angular momentum. Third, time translation symmetry from the conservation of energy. First, we introduce new coordinates for center of mass and the associated total mass of the system, as well as the relative coordinates and the associated reduced mass. When we take all of this and input it in our Lagrangian, we get this. In this form, we can easily see that r is a so-called cyclic coordinate, which means that the Lagrangian does not explicitly depend on r, so it does not explicitly appear anywhere. So we get an expression which is a conserved quantity, meaning it is constant. It has a fixed value which will not change over time. And this is very helpful because it means a couple things. First, the momentum of the center of mass is conserved, meaning it will not change. Secondly, there are no terms containing both the center of mass coordinates and the relative coordinates, so we can separate this entire Lagrangian into two Lagrangians for both set of coordinates. And the Lagrangian for the center of mass is very simple. It just says that the center of mass is moving with a constant velocity, while the Lagrangian of the relative coordinates contains all the interaction between the two masses, which is not surprising because physically that's where the interaction is within the system. So all we have left to solve is this Lagrangian for relative coordinates, which looks like that. So what we've achieved with this is we have used the translation symmetry of the system to reduce the equation to just a single body problem. So next we're going to use the conservation of angular momentum a bit. And to see while it is conserved is rather straightforward. You see, to change an angular momentum, you'll need a torque. And the torque is defined as a cross product of the position and the force, like this, or like this, where I find space. Now with gravity, as with any other central force, the force itself is always in radial direction, so it's always in the direction of a position. So the position vector and the force vector will always be parallel, meaning that the torque is zero, meaning that we have no change of angular momentum, meaning we have conserved angular momentum. Done. The angular momentum itself is also defined as a cross product as the cross product of position and linear momentum. This means that the angular momentum vector will always be at right angle to both the position vector and the linear momentum vector. As we already know that the angular momentum vector is conserved, so it's always fixed, means that the entire motion of the bodies will take place in always the same plane. Maybe you've heard the right-hand rule for cross products. If you fix the cross product, the other two vectors must always remain in a fixed plane. And that's exactly what's happening here. So we will again do a switch of coordinates to make use of this knowledge and use something that is more fitting to this symmetry. So we'll use cylindrical coordinates. And we will choose for the c direction to be in the same direction as the angular momentum L, which will simplify our equation further because c dot is 0 and c will be any fixed value we can choose. So we'll choose 0 again to make it even simpler. This means our equation reduces to this. And finally, we can, in these coordinates, perform the cross product. And as a result, we will get that L is in c direction, because that's what we set earlier. And its value is mu r squared phi dot. And again, that's super useful because now we can express phi dot by means of L, which is a conserved quantity, which is a fixed number. And hence express one variable through another variable r. And this means the equation reduces again to a simpler equation like this, which may not look simpler at first glance, but you can notice that the phi dot has been eliminated and the equation has a single remaining variable r. This is also sometimes called the radial equation because it only contains the radius. So what has happened here? We've used the rotation symmetry of the system to reduce it from being a fully three-dimensional system to a two-dimensional system and then even one dimension. We have a third and final symmetry we can use in that the Lagrangian does not explicitly depend on the time t. So we know from that energy is conserved and we can formulate the conservation of energy in the usual terms. And when we use what we've learned from the last point, then we can set as c and c dot as 0 and phi dot we can express through the angular momentum, which means the conservation of energy reduces to this. Now, finally, this looks way more manageable than what we had before, especially as it's just one-dimensional and we've gotten rid of all the vectors. So this is something we can finally try to solve. Now, we've done a lot of steps, but we've also achieved a lot. This equation is just for a single dimension, for a single variable, and it's only first-order differential equation. So, great progress. We have just formulated the equation we can solve for r and r dot, and if we rearrange it for r dot, it looks like this, using an abbreviation of alpha for some other constants. And we're more interested in the curve itself and not the curve as a trajectory over time. So what we really want is an r of phi and not an r of t. So we can use the chain rule to go from one to the other and finally get an integral for r and phi. Like this. This may look unpleasant at first sight, but really all you have to do is substitute a new variable for 1 over r and then complete the square under the root and you've got a really basic integral. If you're not super familiar with integration and mathematical manipulations, this may sound like a lot, but it's really some fundamental stuff. It's really just a basic integral for the arc cosine. So that's what we get. Now all that's left to do is to solve for r and polish it up a bit. And we start by introducing some new simplifying definitions like these. Then we finally get the solution which we can recognize as the equation for all conic sections. So, ellipse confirmed. There's actually one more conserved quantity in the system which I did not use specifically, and this is the so-called Lenz vector. It already contains information about the curve that is the solution, so the ellipse in our case, because the direction of the vector is from the focus to the perihelion of the ellipse, and its length is proportional to the eccentricity of the ellipse. Actually using this vector in the calculation is the ultimate cheat code you could have for this problem, because it means that you don't have to integrate at all and you don't have to solve any differential equation at all. The reason why I did not use it was because while it is great for actually practically calculating stuff, from a theoretical standpoint, it's not terribly useful. So while it gives us the solution really quickly, there's nothing much to learn from it or to understand from it. But a note on naming here, because I find it quite hilarious. The Lenz vector is also called the Runge vector or the Runge-Lenz vector. And both Runge and Lenz applied it to the hydrogen atom in early quantum mechanics in the early 1900s. But it had already been described a full 100 years before by Laplace for use in celestial mechanics. Consequently, it is also called the Laplace vector or the Laplace-Runge-Lenz vector. However, another 100 years before that, in the early 1700s, Jakob Hermann, a disciple of the Bernoulli brothers, had already described at least a special form of this vector. And then later, Johann Bernoulli had derived the general form of the vector. So it should actually be called the Hermann-Bernoulli vector instead. Or at least maybe Laplace-Hermann-Bernoulli vector? Seems fair. Okay, now as a neutral observer, you wouldn't have made it this far, let's not kid ourselves. But as a neutral observer, you might now be thinking, okay, ellipses, got it, cool story, bro. But all this was actually a really big deal historically. Isaac Newton had not only published his laws of motion, including the famous FSMA, but also his law of universal gravity. And by Newton's time, it had already been observed by Kepler, so it was known that the planets move on elliptical orbits. But then, by combining these two laws, you could also calculate the ellipses, which we just did. And keep in mind, these two laws are relatively basic statements. It's like forces cause accelerations and all masses attract each other. And you take these two statements and put them into a single equation and you get planets move on ellipses. That was mind-blowing. And I think it still is. I mean, come on, it's just a little bit crazy, right?